The topic of today's lecture is relational algebra. Relational algebra is a formal query language based on some mathematical properties. That is, it is defined on a set of by using a set of operations on relations. Before that, we will quickly review the relational model and then we will go on to relational algebra. In the relational model, the first concept is the concept of a relation. Mathematically speaking, we have a set of attributes. Let K equal to A, B and C be a set of attributes, where each is a set of attributes. For each attribute, we have a domain of an attribute, and the domain of each of these attributes is defined by for example, we may have domain of A to be we may have the domain of B and we have the domain of C So domain is the set of values which a particular attribute can take. Now a relation R of these attributes A and B is defined to be a subset of A cross B. It is not A cross B, it is a subset of the domain of A Now let us see what a cross product means. The domain of A can be written out as a table. The domain of B can be written out as another table, but this will be a huge table. This will be a table of large size. And the domain of C will be a smaller table of having only two elements. Now dom A cross dom B is a relation having two attributes. Dom A cross dom B will have attributes A and B, and here we will have all possible combinations of elements of A and elements of B. All possible combinations. This is now a relation will be defined to be some subset of dom A cross dom B. It is not all the elements, but a subset of dom A cross dom B. Okay. So in a relational database, the first concept is the concept of a relation. And that is the only core and basic idea which is used to develop the relational model. A relational model consists of a set of relations. And we have seen earlier that this concept of a relation is a unifying idea which combines the concepts of both entities and relationships of an entity relationship model. And finally, we have seen that all relations may be looked as a table of elements where each table is characterized by a set of attributes. For example, the book relation has got attributes accession number, year of publication and title. Accession number may be all integers less than or equal to say 1 lakh or say 10 lakhs. The year of publication is a 4-digit number which is a standard year of publication, and title is a string of characters of length at most say 50. Therefore, account number cross year of publication cross title is the set of all combinations of such integers, such years and such strings. Among them, the book relation is a subset of all those possible strings consisting of only the valid books which are there in our library. And these are called the attributes, and this is the data which is available in the book relation. Each such row is called a tuple of the relation. Each row is called the tuple of a relation. And after we have designed the database using the ER diagram, we can convert it to the relational database model by getting a set of relations through the database scheme. We saw one example in the previous day. We saw the example of 3 entities in a library system having books, users, suppliers, a borrowed by relationship and a supplied by relationship. We converted them all into, and we had some mapping constraints. We had the key values and we converted all of them into relations, and we got the following database scheme. A database scheme consists of 3 quantities. It consists of a set of attributes. In our library system, the attributes are accession number, year of publication, title, card number, borrower's name, borrower's address, supplier's name, supplier's address, date of issue, price and date of supply. So all the attributes must be specified first. Whatever the attributes are, the types of the attributes must be specified first in the database scheme. Now combining these attributes, we have what are the relation schemes. In our particular case, we had 3 entities, book, user and supplier, and we had 2 relationships, borrowed by and supplied by, and we converted them into 5 relation schemes. The book scheme has attributes account number, year of publication and title. The user scheme has attributes card number, book name and borrower's name and borrower's address. The supplier scheme has attributes supplier name, supplier address. The borrowed by scheme has attributes accession number, card number, date of issue, and the supplied by scheme has accession number, supplier's name, price and date of supply. This was formed from our entity relationship model. This is the set of relation schemes. This gives you the structure of all the relations that you can have. And now we define the relations themselves. We have a book relation which is from the book scheme, a user relation from the user scheme, a supplier relation from the supplier scheme, a borrow relation from the borrowed by scheme, a supplied relation from the supplied by scheme. You can have many more relations from these schemes only. You can have a number of relations from these schemes also. This is like the type declaration. This is the type declaration of the attributes. This is the type declaration of the relations, which we call relation schemes, and this is the actual declaration of all the relations. So we shall use this example while we do our work. Now we come to the relational algebra. We have seen a database scheme. Now we need to process the database. For processing any database, we have to have a query language. And relational algebra is one of the most well-known query languages on the relational model. A relational algebra is a formal query language based on a set of operations on relations. A set of few operations are defined on relations, and based on these relations and a combination of these relations, we have what we call relational algebra. It is also called a procedural query language, and we shall come to some other types of query languages like relational calculus later on, which is slightly different from relational algebra. But for the present, we will concentrate on relational algebra. In the relational algebra, we have got a set of operations, and a set of fundamental operations are defined on the relational algebra. These fundamental operations are predefined relations defined using set theory concepts. We have got some additional operations as well. These additional operations are not fundamental in the sense that they can be derived from the fundamental operations. It is not that these are not useful operations. These additional operations are sometimes more useful and more widely used than the fundamental operations. But the difference between them is that the additional operations can be defined using the fundamental operations. So today we will see what these operations are and how they can be used to query and process a relational database system. So we have got the fundamental operations are select or selection, project or projection, Cartesian product, union, set difference. Union is set union, this is set difference, and this is the rename operation. Among the additional operation, we have the most widely used operation, the natural join. We have the set intersection operation. We have the division or the quotient operation. We have got a generalization of the natural join called the theta join operation. We have got the assignment operation and some others. None of these operations modify any element in the database. They just produce another relation without changing any element in the database. There are operations, additional operations defined to modify the database, which we shall come to later. We will now see first what these fundamental operations are. They are simple operations, but we will see that they are very powerful operations as well. The first operation is the select operation. Now let us see what the select operation does. The purpose of the select operation is to identify, the purpose of the select operation is to identify a set of tuples which is part of a relation, and to extract only these tuples out. So, a select operation is firstly a unary operation defined on a single relation. One example of a select operation is like this. A select operation is signified by the symbol sigma, and it is suffixed by a statement or an expression, and it takes as argument a single relation. So this is sigma year of publication equal to 1992 of book. It says select from the relation book all the books whose attribute year of publication is equal to 1992. That is, select all the books whose year of publication is 1992. So let us see what will happen to the query on this example. In the relation book, we will see that there are 1 and 2 such tuples which have got year of publication 1992. Therefore, this select operation will return a table or a relation containing these 2 tuples only. I repeat, the book has got 3 attributes: accession number, year of publication, and title. If I give select year of publication equal to 1992 of book, it will return a relation which has got 3 attributes: accession number, year of publication, and title. And in that relation which is returned, only those tuples which have got year of publication 1992 will be returned. Let us take another example. This example I will write down slightly bigger. Select accession number greater than equal to this is a subscript. Now this says select all books whose attribute accession number is greater than 56782. Therefore, in the book relation, it will find out all those books which have got accession number greater than equal to 56782, and it will return another relation which has got only those books, and the attributes of the returned relation will be same as the attributes of the argument relation. The expression inside can be combined. In a select operation, you can combine this is a standard Boolean expression. This will select all books whose accession number is greater than equal to 56782 and year of publication is equal to 1992. So a select operation is a unary operation which returns a relation having the same attributes as the argument relation, and only those tuples which satisfy the particular condition which is expressed here. This is another example. Select card number equal to F53 and date of issue is greater than 19/5/92 on the borrow relation. If we go back to the borrow relation, we will see that the borrow relation is of the borrowed by scheme having accession number, card number and date of issue. Therefore, once it says select all those books whose card number is F53 and date of issue is greater than a particular date, only those tuples will be returned. So this is one of the select operation is one of the fundamental operations of relational algebra. The next fundamental operation of a relational algebra is the project operation. The project operation is identified or symbolized by the symbol pi. It takes in one relation as argument and produces one relation as an output. So it is another unary operator, but it is different from the select operator in many ways. We have got the book relation in the book scheme having accession number, year of publication and title. Pi accession number comma title book. This is the formal expression or format in which you write down a relational algebra query using projection. It will first have the symbol pi, and as subscript will be a set of attributes, and its argument will be a relation. These attributes must belong to this relation, and what will be returned is that table or relation corresponding only to these attributes of the relation book. Therefore, pi accession number and title on the book relation will return a table corresponding to this attribute and this attribute. Therefore, if you remove this attribute, you will have a relation having accession number and title only, and all the entries will be kept there. All the entries corresponding to this and this will only be kept, and a relation is always a set. No duplicate entries will ever be there in a set by definition. A set does not have duplicates. Therefore, if by removing this column we form a set of duplicates, then one of them only will be considered. For example, you can have the same book with two accession numbers. Now suppose I project out only the title on the relation book. I will get all the unique titles. I will not get any repetition titles. For example, if I write down this query, then it will return me book. It will return me a table or a relation having only one attribute called title. And this attribute will contain this one: algorithm design, database systems, compiler design, structural methods, programming in Pascal, machine design. But this compiler design will not be there because this is already there. So instead of having 7 entries now, the pi title of book will have only 6 entries, 6 tuples. Let's see 2 more examples. This is an example which combines both select and project. And it is a nested query which says pi title, that is project out title from which relation? The relation that is formed out from selecting year of publication greater than 1992 of book. So from the book relation, we will first select out all tuples having year of publication 1992. And the attributes of this relation which is returned and which forms a parameter to the project relation will have all the attributes of the book. The attributes of the relation which is formed by this select year of publication greater than 1992 of book will actually have all the parameters of book: accession number, year of publication and title. And we will select out only those titles. So this one is actually a query stating find out the title of all books in the library which have got year of publication after 1992. This query means, this is a query corresponding to the question, this is a relational algebra query corresponding to the question, find out all books available in the library which have year of publication beyond 1992 and list their titles only. So only those titles will be listed whose year of publication is greater than 1992. In this one, on the other hand, it does a project first and a select later on. So it projects out only the title and the year of publication attributes of a particular book. So it will list out the title and year of publication of all books in this part of the query. And this relation which is returned will have only two attributes: title and year of publication. And among these attributes, I will select out only those tuples from this relation whose year of publication is 1991. So this corresponds to returning a relation whose attributes are still title and year of publication. These are the only two attributes which are returned here. The relation which is returned, all these operations will return relations only, and the relation which is returned here has got two attributes, title and year of publication. And we know that the year of publication of all the tuples which will be available here will be 1991. We now come to the next fundamental operation. The next fundamental operation is the Cartesian product operator. I have explained Cartesian product before. I'll just quickly review it again. Let us have two relations. One has got attribute A, another has got attribute B, and let the values which are available be let this have three tuples, one with value 1, one with value 2 and one with value 3, and let this have two tuples, one with value A and one with value B. A cross B will firstly have, this is A, this is B. So it is not A cross B that way, it is A cross B. Relation A has attribute capital A, B has attribute capital B. A cross B will have attributes capital A and capital B. And the tuples here will be all possible combinations. and the combinations in this case will be 1a, 2a, 3a, 1b, 2b, 3b. So this, given A and B, A cross B will have the attributes of A as well as B, and the tuples here will be all possible combinations of A and B. We will see a more complete example now, a more involved example actually. Let us have a relation R having attributes A, B. Let us have a relation S having attributes B and C. Now these two attributes are the same attributes because attributes have to be defined uniquely. Two attributes with the same name are actually having the same types. We have defined first only the attributes and then we have defined the relation schemes. Suppose this takes one character, this takes one integer, so this also takes one integer, and this takes a string which is a combination of an integer and a character, so it's an alphanumeric string. Firstly, R cross S will have 4 attributes. 4 attributes, not 3 attributes. The 4 attributes can be uniquely specified and the tuples which will be present here will be all possible combinations of R with S. Not all possible combinations of individual attributes, but all possible combinations of R with S. Example, A1, 3, 1A, A1, 2, 2B, B2, 3, 1A, B2, 2, 2B, A2, all possible combinations of this tuple with this tuples. Not all possible, it is not the same as DOM A cross this is R cross S is not equal to dom A cross dom B cross dom C. It is this tuple as one item combines with this tuple as one item, and therefore we have got all the possible combinations. If this has got m elements, this has got m elements, then this will have m into n elements or mn elements. What I said is that if there are two attributes here, there will be four attributes here. Those two corresponding to A will be R will be specified by R, and those with corresponding to S will be specified by prefixing with S. If there is nothing in common, then there is also no problem. For example, in this example, we had nothing in common. There was nothing in common, but still you can define the Cartesian product. Even if you have it in common, you have this. So it is not necessary that Cartesian product should have anything in common. It just does not matter.
If in one relation, if you declare B as integer, integer, other as a string.
You cannot have B as a relation here and as a string here. I have said before that you first define the set of attributes and their types. So you have defined A as a particular attribute, and you have defined that attribute to be of a particular type. Therefore, now that attribute cannot have two different types in two different places.
Both have two different relations. So I can declare
a particular relation is defined on the set of relation schemes which are defined on the set of attributes. Now, two relations, if they are from two relation schemes, they will take the attributes from a common pool, and in that you cannot have, in this particular case, it takes an accession number from this set of attributes and this takes an accession number from another set of attributes. The set of attributes are first uniquely and globally defined. That is what I was trying to stress in the beginning only, that this set of attributes is first defined and it is a global definition. Therefore, if you have any common attributes, it is from this attribute pool only. You cannot have this as one attribute and this as another attribute type. They are both defined from the same global pool of attributes. The database definition is such that the attributes are first defined, therefore these two must have the same type. In a Cartesian product, they will have different columns corresponding to the relations from which they come from. So let us go back to two of our own relations. The user relation, which has got card number, borrower's name, borrower's address, and the borrow relation from the borrowed by scheme, which has got accession number, card number, and date of issue. So user cross borrow will have all the attributes of user, that is user.card number, user.borrower's name, user.borrower's address, and all the attributes of borrow, borrow.accession number, borrow.card number, and borrow.date of issue. So user Cartesian product borrow will have two such relations having six. This R will now have six attributes. This has got three attributes, this has got three attributes, so it has got six attributes. Now how will we use a Cartesian product? Till now we have done only project and select, and using project and select we cannot combine two relations. We have got project on a single relation and select on a single relation. Now we are trying to answer this query. Find the accession number of all books issued by Rakesh. Let us see how we will use the Cartesian product to solve this particular query. The query is find the accession numbers of all books issued by Rakesh. In the borrow relation, we will not get Rakesh's name. We will get the card number, and we will get the corresponding accession number of the book. We will get the card number and the name of the person and the address from the user scheme. So we will have to combine these two to get from this person I have got this card, this name. I know the person's corresponding card number. Now this card number, for this card number I will find out all the books which have been issued. So first thing that I will do is when I do user Cartesian product borrow, then I will have all possible combinations of the user relation with the borrow relation. Now in this, I will have a combination of card number F53 with card number F35, and that is of no use to me. I do not want any combination. What do I want? I want those users and those people who have borrowed to have the same card number. If they have got the same card number, only in those places will I look at the accession numbers. In the places in the Cartesian product where the card number is different, I am not really interested because that is not relevant to me. So I will select out from there two types of entities. One, I will select out user dot card number must be equal to borrower dot card number. So user cross borrow contains all possible combinations of users with borrows. I am interested in only those tuples which have got the same card number. That is, now I have got an alignment with the corresponding card number here and the corresponding card number here. From there, I will now match out those whose borrower name is Rakesh and accession number is what I want to find out. So here, other than borrower number equal to card number, what do I want? I want user dot borrower name equal to Rakesh. So on user cross borrow, I have aligned out all those which have got the same card number, and I have selected out only those whose username is Rakesh. And now all I am left to do, this is a relation. What will it return here? It will return all the 6 attributes of user cross borrow. And what I want out is only the accession number. I will project out only the accession number. That is, from this cross product, I will align up those which have got user and borrow identical, and I will select out those people whose username is Rakesh, and I will only take the accession number. Sorry, this will be borrower dot accession number, because user does not have accession number. Now sometimes I need not write down these relation names if the attributes do not clash. That is, for attributes which are not common, I need not write this down. Only where they clash, I will write them down. So this query may be simplified and written out like this, without any loss of ambiguity. So an unambiguous query would be user.card number is equal to borrower.card number and borrower name equal to Rakesh on user cross borrow. So using this relational algebra query, we have been able to extract out all account number of all books issued by Rajesh. Now let us understand one thing. If I start interchanging this select and project, I may not get my answer. For example, in user cross borrow, if I first project out the accession number, then I will get all the accession numbers of all the books which have been issued by somebody. And after this, whatever I do, I have got only this attribute accession number. The relation which is returned has got only attribute accession number. This, whatever we have here, is identical to user has got no accession number as attribute. Therefore, user cross borrow, if you project out accession number, and if you borrow out from borrow, if you project out accession number, whatever you get is identical. So please be careful as to, it does not matter whether you interchange the ordering of this AND, because AND is a commutative operation. But select and project, you just cannot interchange them without, it may just change the meaning. Not that it will always change the meaning, but it may change the meaning. So this is a very fundamental operation. The next operation we come to is the rename operation. This is an interesting operation in its own way. This rename operation, let us see what we have done with this rename operation. The question is, find the names of all users who have the same address as Vijay. So let us see the difficulty which we face while trying to solve this problem. Find the name of all users who have the same address of Vijay. How will we solve it? In the user scheme, we have got card, name and address. So we have to look at the user relation. In a normal programming language, we would have put it in a loop and found out all those other people who have got the same name, who have got the same address as Vijay. We would find out the address of Vijay, and from the address of Vijay, we would get the name. All right. So now, in order to do it for this particular relation, we have to do a combination of We will have to do a combination by Cartesian product of user and user. Now, Cartesian product of user and user, if user has got 3 attributes, then a Cartesian product will contain 6 attributes. But we will not be able to uniquely differentiate between these 6 attributes, because both one will have user dot borrower's name, this will also be user dot borrower's name, this will be user dot address, this will be user dot address. What do we want to do? We want to find out from this user and this user, that is, in this user we will find out those names equal, we will select out name equal to Rakesh, find out the address of the person which is here, and find out that this person must have the same address as this person. But we will get into a problem in trying to write out the query here, because we will not know how to identify or differentiate between the attributes. In order to do that, we have what is the rename operation. In the rename operation, we say rename user as user1. Once we have renamed user as user1, now we can use our query quite nicely. Now we have got user and user1, and we have done a Cartesian product of these two. And we want to find out, we want to select out those tuples. Here we will place those tuples for Vijay. We will identify the name of Vijay and the address of Vijay, and here we will match out with those which have got identical names and addresses. So our selection will go like this. We will do a select, and we will select out user dot borrower name equal to Vijay. And what do we want? We want whatever is the address of this user dot borrower name, this address must also be same. So we will select out those tuples which have USR1 dot borrower's address equal to user dot borrower address. So at this point, from this user and USR1, we have got a tuple in which we have extracted out those whose names are Vijay. This has got 6 attributes. Three attributes corresponding to card number, name, address of user, and 3 attributes corresponding to card number, name and address of USR1. In this, we have selected out all tuples which have got Vijay, and we have seen that the address here must match with the address here. So we have matched, the addresses are same, and the name here is Vijay, and what do we want? We want this name out. So to extract that name out, we are now left to do a pi and USR1 dot borrower name. So we have got USR1 dot borrower name, and mind you, in this one Vijay will also come. In this one Vijay's name will also come, not that Vijay's name will not come. Vijay's name will also come. So we have now been able, using the rename operation, we have been able to find out all users who have the same name and address as Vijay. The final two simple operations are the set difference operation. Find the accession numbers of all books. It is the standard set difference. A minus B, those elements in A which are such that they are elements which are subtracted from elements of B. So find the accession numbers of all books which are available in the library, that is, books which are not issued. Books which are not issued will be simply books minus borrow, will give you will this give you the relation? This will not give you the relation, because set difference is defined on two relations which have got the same attributes. So you project out the accession number from here and you project out the accession number from here. Now it is defined on two relations which have got the same attribute. These two relations have got identical attributes, accession number. Borrow pi accession number has got only accession number as attribute, book accession number has got only accession number as attribute, and this will return only those accession numbers which are in books which are there, supposed to be there in the library, and which have not yet been borrowed. Similarly to the operation, we have got the union operation. Find out all books which have been either supplied or which have been issued. Now here again we have to make them attributes common. To make the attributes common, again we will do so union and set difference are defined on two relations which have got identical attributes. So we finish off with the fundamental operations.